So we continue with Robert König from TU Munich, who's going to tell us about quantum error correction at quantum error detection at low energies.
Okay, thanks very much. I would like to thank the organizers first. It's really great to be here. And so thanks for the opportunity also to present this work. So this is joint work with Martina Gschwendtner and Burak Sahin-Oglu and Eugene Tang. Okay, so this talk is essentially about the connection between many-body physics, in particular sort of ground states or low energy states of local Hamiltonians, and quantum error correction and fault tolerance. And since this is mostly a tensor network workshop, I will spend some time discussing what I mean by quantum error correction. In particular, I would like to talk about codes first, about noise models and the task of error detection, and then I will move on to the results about local Hamiltonians. So this will be the first part of this talk. Okay, so let me start with quantum codes. What we mean here is usually an embedding of some logical qubits, some 2 to the k-dimensional space into some larger physical space. So we add redundancy, and somehow by picking such a subspace, we hope to gain robustness in a way. Okay? And you can always think of some unitary encoding map which isometrically embeds this small dimensional space into this larger physical Hilbert space. Okay, and the way we usually specify such a code space is, for example, by fixing local stabilizers, and then you have this immediate connection to Hamiltonians. So you can think about the ground state of some Hamiltonian, say, consisting of commuting projections. And in this class, of course, we have the Tori code and various relatives. So in these cases, we define the code space in terms of such local stabilizers. An alternative view that we've heard about this morning already is to define these code spaces in terms of tensor networks. So if you take the Tori code, for example, we can write down a Mera description, which is essentially an encoding circuit for this code. So it maps these logical degrees of freedom to physical degrees of freedom on n qubits. But you can also think of this as just contracting a tensor network where this dangling edge is essentially free, so you can put any logical state there, and in this way you can define the code space. Okay? And the holographic code is another example of this kind. So here we put the logical degrees of freedom on these red edges, and we contract the tensor network, and we end up with something on the boundary. Luckily, I don't have to explain this because Jens did this very nicely. Okay, so in this context, of course, there's this conjecture that somehow CFTs are supposed to be quantum error correcting codes, and that was part of our motivation. We wanted sort of more concrete models, or sort of understand how general this can be. So I won't say too much about this, so let me move on. So once we fix the code space, we should think about what kind of errors we want to protect against, or what kind of noise this should be good for. So the kind of noise that I would like to consider in this talk is what we call d-local probabilistic noise. So this means that, general noise is just a CPTP map on these physical qubits, and we assume that essentially with probability Pf some error f happens. These errors have a boundary norm, and they have support of size d. So this is important. So this can be anything like, for example, a d-qubit Pauli operator, but we don't have any assumptions on the support apart from the size of the support. In particular, the support can consist of disconnected regions. Okay, so this can be, in a sense, non-local operators. The support size is d. So this is general d-local probabilistic noise. Local, d-local only refers to the support size and not to geometric localities, say, on a lattice. Okay? And so that's the noise we want to study. It's relatively general. I have to say it's not the most general type of noise you could consider, but it includes, for example, random Pauli noise, which is often considered in quantum error correction. Okay, and one other thing I should say here is that this kind of noise model is difficult to correct for, more difficult than, say, erasure errors, because when you have an erasure, you essentially learn where the error occurred, and this is not the case here. Okay, and in this way, our work is a little bit different from previous works in this direction, which mostly dealt either with erasure errors. In that case, you can talk about entanglement entropies and have all these entropic recoverability arguments, or they only considered errors on fixed subsets of qubits. Okay, and here the subsets are not fixed. Okay. So now, what do I mean by error detection? So I fix the code space, I have some noise model, and now I want to introduce some operational task, which we want to evaluate with respect to this noise. So basically, what we want to do is we just want to decide whether an error occurred. So this is a very simple primitive. It was introduced very early on. So these are two figures from this paper. So the idea is that you can somehow measure and decide whether an error occurred or not. If the measurement says no error occurred, you should have the original state in the code space. So for example, in this case, if nothing happens to the code space, if you project back here, you have the original states. But this would be an undetectable error because this error maps one code state to the other code state. So even if the outcome is you're still in the code space, you could have changed the encoded information. So this is something you want to avoid. Okay, so this is what we consider. This is very nicely connected to, say, topological order, but it's an operational task. So how do we actually do this? So suppose you have some code state, you have this noise acting, and then you have to measure, so you have to do a binary measurement to decide whether an error occurred. The natural thing to do is to try to project onto the code space. Okay? And if the outcome is that no error occurred, if you project it onto the code space, then you say this is no error, and what you want is that in that case the post-measurement state should be the original state. Okay, so that's the definition of an error detecting code. So when you look at the post-measurement state after applying the noise and projecting onto the code space, this should be exactly the same as this initial state that goes in. Okay, so conditioned on this outcome, you want the original state. Okay, and there were many constructions, in particular using stabilizer codes to get this property for all states in the code space. Okay, so we want to relax this notion because it's very rigid. It only applies essentially to stabilizer codes. So there are many things you can do. So the first obvious thing is you can demand that this is only approximately true. So you recover the original state up to overlap epsilon, say. But you can relax this further, and in fact, that's quite natural. So instead of demanding this to be true for all states in the code space, we're only going to demand this for states for which you actually get this outcome with a non-negligible probability. Otherwise, you don't care about it anyway. Okay? So this is going to be the definition I'm going to use. We call this an epsilon delta approximate error detecting code for this noise channel. What you want is that for every state in the code space, which has the property that after applying the noise, you still have overlap delta with the code space. You want this property that conditioned on getting outcome you're still in the code space, you still have overlap 1 minus epsilon. Okay, so there are two parameters that we can play with, but basically we want both these approximation parameters to go to 0 in the thermodynamic limit. So that's going to be the goal. So this would be a code that protects against this particular noise. If the code protects against any d-local probabilistic noise, then we call this an epsilon delta NKD code. So what do I mean by this? So epsilon delta are these parameters here, which tell us how approximate this is. N is the number of qubits, K is the number of logical qubits, the code dimension, and D is this d-local from the noise. So such a code protects against any such d-local probabilistic noise channel. Okay, so actually the topic of the talk is, are there such approximate error detecting code within low energy codes and subspaces of certain Hamiltonians? And again, we want sort of these parameters to go to 0. Okay, so this is basically a summary of the results that I would like to discuss. So first we have a no-go theorem. It says that if you just take the ground space of some local gapped Hamiltonian, this is not going to be an epsilon delta NKD approximate error detecting code. So that's discouraging. But then we have two ways of getting around this. So either you go to excitations. So if you have the low energy subspace of any gapped local Hamiltonian, you actually get relatively good codes. You get polynomial distance, this D local I call the distance. D can be any polynomial arbitrarily close to linear. And we have the same, so then the third result is a calculation for the Heisenberg model, which is gapless. In that case, we also find codes with the same essential parameters. Okay, so I will first try to present these results in more detail and then try to explain a little bit of the proof. You might wonder what I mean by exactly 1D local gapped Hamiltonians. Essentially, it refers to the mathematical framework we use to describe this. So this is a result essentially about injective matrix product states with constant bond dimension. This is a result about the so-called excitation ansatz. And in the last case, we use beta ansatz tensor networks. Okay, so let me start with the first statement. Okay, and so for this, I have to briefly recall what we mean by injectivity. So we're going to look at matrix product states of this form. So we have some tensor A, it's translation invariant, and we have some boundary tensor X. And injectivity just means that this transfer operator is gapped. So we can normalize it to have largest eigenvalue 1, and then the second largest eigenvalue should be strictly less than 1. And this has various nice implications, for example, decay of correlation functions, and so on. The way I'm going to use this is to actually just take this operator, exponentiate it. We can diagrammatically represent this in this way. So this is the else power of the transfer operator. And because it has maximal eigenvalue 1, there's essentially just one rank 1 operator in the Hilbert-Schmidt space, plus something which now decays exponentially with L. Okay? And this kind of approximation we're going to use. This is very convenient. So that's sort of the implication. Okay, so the first question is, can we have, well, I should say that these injective MPS, they're of course known to be ground states of gapped Hamiltonians. There's this apparent Hamiltonian construction and so on, and there's a Hastings result. So now we ask basically, can we fix this tensor A such that the transfer operator is gapped? So we have an injective MPS. And can we now choose this boundary tensor in such a way that we get a code space? Okay? So we're going to try to choose some subspace of boundary tensors. And the answer turns out to be no, this doesn't work. No matter what subspace you choose, you always get a code with constant distance. Okay, so again, what this means is if you want this approximation parameters to go to 0 for n going to infinity, then this locality parameter for the noise has to be constant. In fact, it's upper bounded by a constant type, the logarithm of the bond dimension. So if you have constant bond dimension, you don't get good codes. Okay, and one way of interpreting this is to say that you have no topological order in 1D. I will get to that. Okay, so the second result, now we go beyond ground states, and here we use the excitation ansatz. So this is a tensor network state that looks like this. So we have a superposition of such states, which are essentially the same as before, but you have an insertion of some tensor B at the jth location. You superpose in a way that you get momentum eigenstates. Okay, and this tensor B can be momentum dependent itself. So it turns out that this kind of ansatz is very good. It allows you to describe momentum eigenstates, so quasi-particle states of gapped Hamiltonians. So this is a result by Hagemann et al. Okay, so the question is, can we now use such states to define codes? Okay, more precisely again, we now you start with such a state, and what we're going to do is we're going to vary the momentum, okay? And we're going to ask, is there a set of momenta, so can we fix within one band a set of momentum eigenstates in such a way that we get an approximate error detecting code, okay? And of course, if you think about this, it shouldn't be possible to pack too many different momenta eigenstates into this code space, otherwise you can describe localized wave functions, and then this is not going to be a good code in terms of distance. Okay? But essentially what we find is that you can fix any number up to, I guess, polynomial number of momenta, and you get a code with the following parameter. So epsilon delta, they go to 0 at the polynomial rate as you want for n going to infinity. You have a logarithmic number of encoded qubits, and the code distance can be any polynomial with exponent strictly less than 1. Okay. So now, so that means you can essentially construct such approximate error detecting codes starting from an injective MPS. So you go to the parent Hamiltonian, then you find this tensor which describes the quasi-particles, and then you fix a set of momenta. That's sort of a recipe. Okay, so what about the third result? So we have this, we consider the Heisenberg XXX model. So here we just consider a very particular subspace. So we want something which has non-zero momentum. So this is actually the state with the lowest energy that has non-zero momentum. And so this is a gapless model, so we can actually find many other states that have the same energy. We can apply a spin lowering operator to the state, and this will generate a representation of SU2. It's a representation with angular momentum n½ - 1. These are all eigenstates of the Hamiltonian. They're all momentum eigenstates. Okay? So now we're going to ask, can we sort of pick a certain number of descendants? Every R here corresponds to the magnetization of that state. So these are all momentum eigenstates. Can we choose a code space in such a way that this is an approximate error detecting code? Okay, and the answer turns out to be yes. So again, we get a code with essentially the same parameters, so polynomial decaying approximation parameters, logarithmically many encoded qubits, and almost linear code distance. Yes? We only looked at this. Maybe I can get to that later. Okay. Then there are some things we want to do, but okay. So now let me try to tell you a little bit about how these things are shown. So for the first two things, of course, we need injectivity. Oh, I should have said this excitation ansatz states that only holds, of course, if the ground state has an injective MPS ansatz, then you can describe the quasi-particle excitations. Okay. So also here we have this injectivity property. Okay, so first about this no-go theorem. So the first observation, you don't really have to read all this, is that if you want an approximate error detecting code, the states, the reduced density operators of code states should be locally indistinguishable. That's sort of intuitively obvious. So what you can do if you want to show that something isn't a code, you just find two states such that the reduced density operators have large overlap. Sorry. I guess small overlap. Okay, so then they are locally distinguishable. That's what you don't want. Okay, so let's take two states of this kind. So an injective matrix product state, and we vary the boundary tensors. So we have X or Y here. And we want to show that reduced density operators have small overlap. So intuitively what you can say here is because of injectivity, all this information about X, it sort of decays rapidly. So in the bulk, the states will look very similar. Okay? And the information about X should somehow be accessible near the boundary. And because the states are assumed to be orthogonal, we should actually look at the reduced density operators on near the boundary. Okay, and this will give us the no-go theorem. Okay, so we're going to compute the overlap of two such states with respect to sites located near the boundary, so near these boundary tensors. And you can use the flip operator to write down this kind of tensor network diagram to express this. Okay. Now we can actually let the swap act everywhere. Then you get a slightly different expression. And now we have to argue that this is small. And what can we use? We can use this injectivity property. So first you observe that in this diagram you have 4 occurrences of these powers of this transfer operator. And for each occurrence you can replace the power of the transfer operator by this rank 1 projection plus this exponentially small decaying term. So you get 16 terms. Okay? And of course these terms are going to be small if you choose the parameters right. So the question is really what happens with this term. So suppose we replace every occurrence with this rank 1 projection, you get this diagram. So why is this small? Well, let me ignore this inner part for a moment. Then these outer diagrams, they just correspond to the overlap of the states, if you again use this property. So you know that this is a small scalar, and you can also argue that this has constant norm, so you get that the overlap is small. So that's the idea of the no-go theorem. It just uses this injectivity property. Okay, so now we want to actually construct codes. So now we need a sufficient condition. And this condition is something like this. So this is sometimes called approximate nil-Laflamme conditions. So essentially what you have to do is you fix an orthonormal basis, and you have to think about expectation values of d local operators with respect to the spaces, so matrix elements. And so essentially that's what you need to compute. I just would like to mention that this is connected to the eigenstate thermalization hypothesis, which looks very similar, and is actually used in this paper. So for the excitation ansatz, that looks like this, for example. So we have these superpositions, and if you take an expectation value, we get a sum. And here I just assumed that the error acts on 2 locations, but this is just for the purpose of this talk. So when you have this diagram, you can again go in and look for powers of the transfer operator. And this is a little bit tedious because you have to be very careful about where you make these substitutions. You can't do them everywhere. You need large enough powers. But then you can again show that these overlaps are small, and that's what you need. Okay, maybe I will skip this. So just one thing I would like to mention is that we need these left and right eigenvalue equations of the transfer operator, and we also need to do a certain gauge fixing of this excitation ansatz states, which was developed in these papers. Okay, so finally for the Heisenberg model, again we would like to compute matrix elements with respect to some orthonormal basis. It turns out that this highest weight vector, you can write down an MPS representation. This spin lowering operator has an MPO representation. If you put this together, then you can look at these basis states, and they have this kind of tensor network description. So then when you compute expectation values, you have to compute diagrams of this kind. So what we have to understand in this case is we have to understand the Jordan structure of these generalized transfer operators. So these are now not injective MPS, so we don't have this simple property of the spectrum. But we can actually analyze this. We find that the spectrum in this case is given by these points on the unit circle, and we also know the sizes of the Jordan blocks. So again, by this we know how powers of these transfer operators grow, and that's what we need. Okay, so this is essentially what I wanted to tell you. So we have these 3 results, and there are some open questions. For example, we can try to go to 2 dimensions. In fact, this is something that's already been studied. There are sort of PEPS analogs of this excitation ansatz. And for this gapless model, one interesting question would be to try to generalize this to general models that might be solvable using this algebraic beta ansatz. At least there we have some MPS descriptions, and the challenge is to understand the structure of these transfer operators. Okay, and perhaps, I mean, this was our motivation, perhaps this can be generalized further, and we can say something about CFTs. And I think the last example is particularly promising. It looks like this has something to do with descendants of primary fields in some CFT. Okay, thanks very much.
Thank you. Okay, very good. We're doing good with time, so there's time for questions. Maybe we can start with Jens.
Very nice. And when you think of like 2D settings, I mean, is that obvious? Even to, I mean, how would you find out in the first place that the Hamiltonian is gapped to make sure that you can use these techniques of using like excited states to make approximate error detection?
I think this. So the first question is, I guess, about this excitation ansatz.
Yeah.
And I thought this result by Nachtigall et al. That I mentioned, it actually also applies to high-dimensional lattices, if I remember correctly. It's okay. But then, yeah, then it's a calculation. I mean, you just. So,
in the course of the talk, there was a question from the back, and it was postponed.
Oh.
He answered. Okay, good. Yeah, one more.
Do you have any idea of the usefulness of these codes? Like, are they would be easy to encode or decode, or fault tolerance measurements of the syndromes?
Yeah, that's a good question. I mean, we haven't really thought about this. I mean, certainly, if you want to do error detection, you don't want to do a global measurement of whether you're in the ground state or not. That might be hard, but in terms of code distance, I mean, they're of course much, in a sense, worse than sort of standard stabilizer constructions, which have linear distance and not sublinear distance like here. So as soon as you have, in a physical setting, of course, IID noise on every qubit, then this is not good enough, because in expectation you're going to get a linear number of errors, and not. So I'm not sure whether, like, maybe not for large systems. Maybe there's some intermediate regime where it makes sense to use this, because they're just low energy states. But asymptotically, they're not good codes in the coding sense, I would say.
Okay, one last question, but please wait for the microphone.
Can you get a similar construction for thermal state rather than ground states?
Thermal states?
Yes, so as a matrix product operator, and then...
I mean, usually if you want to encode quantum information, we would like to use pure states, but so, I mean, maybe if you want to encode classical information, it will make sense to also use thermal states, perhaps. But then the figures of merit would look a bit different, probably. But I don't see why not. Like, this similar calculation should be possible, I guess.
Okay, I think it's time to conclude. So let's thank Robert again. Before we